In machine learning classification, you're going to often encounter problems where the target variable you're trying to predict often occurs infrequently. As a result, it can be difficult to develop a good prediction. This is a problem of imbalanced distribution, and many machine learning techniques struggle to produce meaningful results as a result. Imbalanced data is something you'll encounter in a classification problem, in which the number of observations per class are disproportionately distributed. These problems can be difficult to solve. However, there are several sampling techniques that you can use to leverage to improve your results. In this lesson, we're going to introduce the Imbalance Learn, or the IMDb Learn package. This is an excellent package which offers a variety of sampling techniques for dealing with this problem. Let's walk through some examples. First, we're going to generate a classification dataset using the Scikit-learn dataset package. Here you can see we have 5,000 records, 2 features and 3 classes. We've also assigned the weights to each class. You're going to go ahead and assemble that into a data frame so you can see the data. There you go. You can see the features and the target variable. Now let's go ahead and use the pandas hist function to visualize the classes. All right, there you go. That's a heavily imbalanced data set. Now let's apply what's called oversampling. For this, you're going to use the naive approach known as random oversampling. You're going to upsample the minority class. That is, the sample with replacement until the number of observations is uniform across the classes. As you might imagine, this approach should give you a pause depending on the scale of upsampling you're doing. First, from the oversampling package of Imbalance Learn, you're going to import the random oversampling. Now let's apply the oversampling to X and Y from above. Next, let's go ahead and visualize the distribution. As you can see, we've actually increased the size of the minority class to be uniform with our minority class from the random sampling. Another common oversampling technique is called SMOTE, or synthetic minority oversampling technique. In this case, you're actually going to generate new observations from within the existing feature space over the minority classes. Now let's go ahead and try an undersampling technique. Again, you're going to start with a naive approach to randomly undersampling the majority class. This time, you're actually throwing out valid data in the majority class until the number of observations is uniform. As with our oversampling from above, Imbalanced Learn offers a random undersampling as well. You can run this and see again, it's a uniform distribution across the classes. Note, however, that we just have over 60 observations per class. Because of the infrequency of the smallest minority class, you threw out a large percentage of the valid data. Because of this, it's probably a good idea to consider other methods for this data. There are other undersampling techniques to explore, including k-means and near-miss. If you're encountering an imbalanced classification problem, be sure to check out Imbalance Learn and explore some different sampling techniques.